Okay, so welcome everyone to the second part of lecture 13, which is the first lecture for proving the Kato conjecture. So in total that means that we're going to make 4 videos for you showing you the way towards eventually completing the proof of the Kato conjecture. I'll do, as with every good series, I'll do a short recap what happened last time. If you really take it seriously, you're watching it like a good Netflix series. Of course, you didn't stop. You just watched the second video immediately after the first one. But these guys here in classroom, they had 2 days of break. So it's kind of fair to recall what we're searching for, right? And so there are 2 operators that play an essential role in last lecture, and they're also going to continue playing an essential role in all of the remaining lectures. So there was the operator theta t. Theta t was just t times the resolvent of L acting on divergence of AF. Okay, so that was the theta operator. And then there was its principal part, gamma t, which was a vector. It was just a function actually, which was obtained by applying theta of t to the unit vectors. Okay, so the unit vectors viewed as constant functions, I applied theta to all of them. That gives me a c to the n valued function, and this action was explained through off-diagonal estimates, and that thing was called the principal part. Okay, and the very reason why we are working with this operator theta is the following identity. If you apply theta of t to a gradient of a h1 function, then you see that you're gonna pick up divergence A gradient, so that gives you the operator L back up to a minus sign. And so the thing was that this would produce for you minus t L 1 plus t squared L to the minus 1u. Okay, and this identity over there, forgot to put out my colored chalk, this was called 13.2 in the previous lecture. Okay, and so remember that we introduced this operator because we knew from the lecture that Sylvie gave us that the Kato conjecture is equivalent to a square function estimate. Okay, and the square function estimate in the language of Sylvie's lecture was put on this guy. So you wanted to build a square function of this guy, and you wanted to control it by the gradient of u. And the reason why with you I introduced the theta of t acting on vector fields last time was that through the use of theta and this identity, the square function in the Kato conjecture becomes an operator acting on gradient of u. So it's all phrased in the variable gradient of u. Okay, so the goal of this 13th lecture is to prove, the goal for the Kato conjecture would be to prove the square function estimate theta of t grad of u squared dt over t controlled by gradient of u. Okay, that's an identity that last time we called 13.1. Okay, and then I explained to you the general strategy coming from papers of Chris Journet and Sems using a principal part approximation and a Carlson measure estimate, and we agreed that this week is going to be principal part approximation time, and then next week is going to be Carlson time. Okay, and so let me wrap up that for you. So, and in lecture 13, we confine ourselves to the principal part approximation. Okay, and let me recall for you that principal part approximation means that we have a square function bound, but we take the theta and we subtract off a multiplication operator, which is precisely the principal part, acting on the dyadic averages at the same scale, And this object should give rise to a square function bound. Okay? So that's what we saw last time. We want to prove this in lecture 13. So I take my favorite color and just put a box around it. Okay, so at the end of today's lecture, we should be in a position to have this estimate, and then we can say that we made it halfway towards the proof of the Kato conjecture. Okay, so it's not the first time, because it's the second lecture, that we talk about these things, and there was an intermediate result that we obtained already in the first part of lecture 13. And this intermediate part was what I'm going to recall for you next. So far, we know it was the last result of the lecture on Monday, and it was a smoothed version of this principal part approximation, where we had to smuggle in an additional smoothing operator right at that point. Okay, because our estimates were poor for large T and they were not sufficient for bounding anything of this type. Okay, so the result that we had was 310 was a proposition. Was it 310? Yeah, I guess so. And the proposition said that we have a smoothed principal part approximation. So we have the principal part, but it was acting on smoothed out vector fields by means of a smoothing operator pt, and we controlled that by f in L2 norm. Okay, eventually capital F is always a general L2 vector field. Gradient of u is always the gradient of h1 function. These constants c, they only depend on dimension and ellipticity. Okay, so that's what we have so far. And to end sort of this rather long, but I think useful for you, what happened last time section, let me say what was PT. Well, PT was the resolvent of negative Laplacian on Rn, and then there was an accompanying operator Qt. Qt was T times gradient. Okay, these guys were useful. Okay, so that's what we know, and now we have to go on. And so what we have to do is we have to remove the smoothing. Okay, the smoothing has to go away. And you see, so let's phrase it like this. We need to get rid of PT. Okay, so how are we going to do that? Well, of course you know that mathematicians and analysts in particular are magicians. When they don't like terms, like I do not like the PT anymore, even though it was my friend on Monday, but who cares? Right? And I can just write down a new formula where the PT disappears by adding and subtracting zeros so that it works out. Okay, and then I have to handle the error terms. So, that's what I do. So I take theta t minus gamma t times at. This is the term that I want to control. And so, unfortunately, I only have this one. Okay, so this is going to be an equality in the bounded operators on L2. All these operators are bounded operators on L2. So this is what I can do, but it's not the same. Right, so this is where my magic breaks down. But I'm going to create error terms and I'm going to handle them today. So on the level of theta, I need to handle theta times 1 minus pt. And then you see on the level of theta it's fine. Theta t minus pt plus pt. And then on the level of gamma t times at, I also need to handle 1 minus pt. Okay? And then you see with the gamma t's is also fine. This gives minus gamma t at, the smooth version with a plus, smooth version with a minus. Okay, so that's the three terms. I want to control square function of this. I do instead all the three others, and at least the first one is fine, right? So this is what I can do. This is 3.10. All right, so this equation is what? 1313. So what you will see is that the main work with the operator theta and the principal part, the main work was what we did last time. It will turn out, and I strongly advise you to follow under this particular idea, the lecture, it will turn out that I will use very little, extremely little information on the principal part and the theta operator when I'm doing these two terms. I'm using more like general harmonic analysis and very easy arguments as long as the operator L is concerned. Okay, so therefore I tend to say that these are sort of error terms that do not have so much to do with the Kato conjecture itself. Okay, you will see that, but so this is like a teaser for you to see what you should be paying attention to when I do the proofs. All right, and so let's go and do the first of the error terms, so do the second term in 1313. Okay, and the proposition says that I have a square function estimate for the second term. So theta of t 1 minus pt, I only do it on gradient fields, which is fine, dt over t, and I claim that this is controlled by L2 norm of the gradient. Okay, that's the proposition. And so how are we going to prove it? Well, in the proof, I will start just by writing out things. Okay, so theta of t applied to 1 minus pt gradient of u. Theta 1 minus pt, you know, we saw it last time, is defined through Fourier multiplier if you want so, and it commutes with the gradient operator. That's one of the remarks that I showed you last time. So the gradient and the pt, they commute. This was, I think, remark 13.8. Okay, so I can put theta of t back together with a gradient, and then I put 1 minus pt on the function u. Okay, and so to stress how little information I'm using of the whole machinery for estimating this term, I will undo the writing that I did over here and reintroduce just the resolvent of L with the first term. Okay, so this is going to give me, by this 13.2, this is going to give me minus TL 1 plus t squared L to the minus 1, acting on, well, this is 1 minus the resolvent of the Laplacian, right? And so 1 minus the resolvent of the Laplacian, you know that you can always write it as minus t squared Laplacian times 1 minus t squared Laplacian resolvent acting on u. Okay, it's the usual trick, identity minus 1 plus L to the inverse. You factor out, you get precisely this. Okay, or you do plus identity minus identity, then you work backwards, you see that that's true. Good, so what should I do next? I want to bound the square function by something that involves the gradient. Okay, so now I remove the gradient. So what I'll do is I write this Laplacian, I write as divergence of the gradient, and then I throw the gradient to the other side. Okay, so this gives me minus TL 1 plus t squared L to the minus 1, and then it's going to be minus t squared divergence 1 minus t squared to the minus 1, and then it's gradient u. Alright, so this begins to look promising. These guys here, minus divergence resolvent, they are the adjoints of Qt. Okay, maybe I want to pass also the divergence to the other side. Maybe that's better. Okay, I can do that because these objects all commute in Fourier space. Okay, and then if I do it like this, then you see that I have the adjoint of Qt sitting here, almost because the adjoint of Qt comes with a t, and here I have a t squared. Okay, so let me get rid of that first. T squared goes away, and I put the t squared here. Then this is still correct. Just change the t. And so in this notation, this here is Qt star. Alright, and this other term, let me take different color for this. This other term, I can do the usual +1 -1 trick. If I do +1, t squared L will give me an identity. Okay, so let me put the minus sign out. I do +1 gives me identity. Okay, so this is identity, and then -1 gives me resolvent. Okay. Alright, so this is as long as I have to massage the term. I'm done now. Now I just take norms. Alright, so theta of t, 1 minus pt grad u in L2 norm is bounded by. And now you see how generous I can be in this estimate. Well, I just sent L back home. Right? This is 1 minus resolvent of L. Who cares? It's an operator by M accretivity. It's an operator bounded in norm by 2. Because it's the identity, and the resolvent is bounded by 1. So I just put a 2 here, and I put the L away, and I just stick with the Qt star acting on the gradient of u. Right? And now I want to bound the square function of this guy, meaning I want to square that expression and integrate in t with respect to dt over t. Well, I just need to bound the square function of this guy. But this I already did on Monday. Was in Lemma 13.9, the second part, the adjoint square function estimate. Okay, the square function of this guy is already bounded, so I'm done. Okay, so conclude by adjoint square function estimate in 13.9 part B. And that's the proof. I threw away all information coming from L. I just did something for the Laplacian. I did something I could have already done in lecture 4. Questions? Please. These would be curly Laplace operators, but you can just view them as the multiplication operators on L2. Yes. Under the Fourier transform. They would be curly Laplace operators when they are sitting like this. So this is a curly Laplace operator, which is perfectly fine because it's a curly Laplace operator acting on a h-1 function, because L2, h1, L2, h-1, curly Laplace. Fine. They're curly Laplace, but I don't want to make a ridiculous symbol with a wobbly Laplacian. Other questions? Okay. Well, now I would just like to check. Let me check once. Did I do the theta with a plus or with a minus here? Last lecture. Was there a minus sign or a plus sign? Can you check for me? Well, I will check myself. With a plus? Okay. So I didn't do anything wrong. Okay, then my signs are correct. Very good. Huh? With a minus? There was a minus last time. Oh, so I did all signs wrong. Okay, so last time there was a minus sign. Okay, well, it doesn't matter. So then there's your plus sign. Okay, thanks, guys. So then there's this becomes a plus sign, and then this minus goes away. Okay, thanks. Now everyone watching the video hopefully could have fun. You're gonna leave that in the video? Yeah. Just show my stupidity with a minus signs to everyone. So fine. Okay, but the proof didn't change because I took norms. Okay, but that is correct over there. I'm happy with that. Okay. So you see, easy proof just goes back to the Laplacian. Now I want to do the same kind of things with the second term in 1313. Okay. So I claim that the second term in 1313 is more complicated. It's more complicated, but somehow the gist of the matter is the same. I will just remove all parts that come from the operator L, and then I will prove a result from, if you want so, classical harmonic analysis. So what do I mean by that? Or why? How can I do it for this other term? So it's this term over here. Okay, it will not be enough to just throw gamma t 80 away. This is for sure. But there is a trick. Okay, and so the trick is to start like this. I claim that AT, dyadic averaging operator at scale t, is a bounded operator on L2. I can apply it twice. What happens? What happens if I do dyadic averaging at scale t twice? Imagine I average once, then I will create a function that on this grid of dyadic cubes at scale t is constant on every cube. And then I average again, nothing is going to happen because average of a constant is the same constant again. Okay, so AT squared is AT. Okay, and then I'm gonna use that and take the second term, and I'm gonna write gamma t dot AT 1 minus PT. I'm gonna write as gamma t AT 1 minus PT, and I'm gonna smuggle in another AT. And that is okay, because if you multiply it out, this is going to be AT squared, which is the same as AT over here, and then it's going to be AT PT, which was over there. Okay, so I can write it like this. And then we have seen in the lemma, when I started sort of introducing you, we tried to get to know a little bit this principal part. This is lemma 13.5. We saw that these operators, they're uniformly bounded on L2 by lemma 13.5. Okay, uniformly bounded, I always mean they are bounded on L2 and the bound is uniform with respect to t. And this is precisely what this lemma 13.5 said. All right, so if I want to control the square function of that guy over here, well, I can take L2 norm, which I do in the square function. I can throw that guy away. That sounds ridiculous at first sight, but if I happen to be able to manage the square function of the other guy, then this is still sufficient, similar to what has happened over there. Okay, and so this is what I will exactly do. So I want to bound this. Okay. So we just need to bound the square function of this, and this has nothing to do with elliptic operator divergence form. It is just about, if you want, so comparing smooth and dyadic averages. Think of this PT as a smoothing operator. It's a convolution with a okayish kernel. We could have also taken convolution with a smooth function supported in a unit ball, then this would be really smooth averaging. So somehow this is about proving that dyadic and smooth averages are close. I'm going to be more precise at the end of the lecture, or what I mean by that. Okay, but it's a property just of these two averages operators, and this doesn't play a role. Okay, and so if I want to bound this, then I'm going to create functions that are constant on dyadic cubes. Okay, and at the end of the day, I'm going to apply the principal part approximation to a gradient field. So I will need a reasonably good estimate to bound the average of a gradient field on a cube with absolute value outside. Okay, so that's a lemma that I need before I can start the proof of this third term. So this would be 1312. Okay, 1312, a lemma that allows you to bound the average of a gradient. So suppose Q is a dyadic cube. Suppose U is H1 on Rn. You could also take it H1 on the interior of the cube if you want. But H1 Rn is enough for what I'm trying to say. And so the lemma says that if I average the gradient on U, I take a square of that, then this I can bound by a constant over the length of the cube times the product of the L2 averages of the function and its gradient. Okay, and I should put dx's everywhere because that's what we do in the lecture notes. Okay. Okay. So that's my little lemma for bounding averages of gradients. Proof. How do you prove such a thing? Well, to give you an idea of what's really going on, imagine that the U would be such that its support would be a compact subset of my cube. If the support of U would be sitting inside that cube, then I could just integrate here using Fubini theorem, and in each direction I just do fundamental theorem of calculus and I pick up 0 because the function would be 0 on both ends of the cube. Right, so if the support of U would be inside of Q, this average would be 0, and that there would be nothing to prove, of course. Would be still true, but would be useless. Right, so that gives you the idea that somehow you have to play a little bit around with the support of U, and maybe you should introduce a cutoff function that is supported in a compact subset, and then you look at two cases. You look at the boundary case and you look at the interior case. Okay, and so for this proof I'm going to work with a threshold. Alpha is going to be a number between 0 and 1, and the reason why I'm working with this threshold is that I'm going to put eta a smooth function, and the picture is like that. So you have your cube. This guy is going to be my Q. And then inside of that cube is sitting a smaller cube. I'm going to make the smaller cube in red. Okay. This smaller cube, this is 1 minus alpha times Q. So it's a concentric cube, slightly smaller, and the enlargement or the smalling factor is 1 minus alpha. So this is because I pick alpha between 0 and 1. Okay, and then the function eta, the smooth function eta that I want to have, it should have the following properties. It should be equal to 1 on the smaller cube. It should have support in the larger cube. Okay, so the support of eta is something like this, maybe. Okay, and then there should be an estimate, and the estimate should be the usual one. So eta is bounded, and the gradient is comparable to the distance of these two sets, and the distance of these two sets is about alpha times the length of Q. So alpha times length of Q times the gradient of eta should also be bounded uniformly. It's the same kind of construction for test functions that we used when Robert showed you off-diagonal estimates. Okay, you would obtain it just by smoothing out the characteristic function of the red cube with a mollifier, and the mollification parameter you would take something like alpha length of Q over 4. Okay, you trust me on this, you can make the construction of this test function. All right, so that's what I'm going to use, and the alpha I have to pick. By now you know the game. At the end of the day I want to pick the alpha such that my stupid additive inequality from stage 1 becomes multiplicative, as always. Okay, so I'm going to write the claim. I'm going to write in a short way. I'm going to call x the average of the gradient. Okay, so x is, now I need how many colors? 3 colors. So x is going to be the average of the gradient. And the claim I want to prove is this is bounded by constant times the length of Q times the average of the function squared to the 1/2. So this is y to the 1/2. And then average of the gradient squared, this is z to the 1/2. Okay, this is my claim. This is what I want to prove. All right. So I can assume, of course, I can assume that z is positive. Because if z would be 0, then the gradient would vanish everywhere in the cube, and then already the left-hand side would be 0, and there's nothing to prove. Now I'm going to take the function, or the gradient. The gradient is what I want to bound the integral of, and I'm going to write the gradient as eta times the gradient plus 1 minus eta times the gradient. Okay, so I distinguish between parts that are supported near the boundary. This is this one, because 1 minus eta vanishes on the entire red cube. And then I have the rest. Okay, so then I'm going to average the whole business in Q. So I'm going to average here. And I'm going to average here. And then I'm going to integrate by parts. I can integrate by parts this first term, because eta has compact support in Q, so there's no boundary terms. So when I integrate by parts, I can turn this into a minus grad eta times u. Integration by parts, or definition of the weak derivative. Okay, so if I do it like this, then I can take absolute values everywhere. I take absolute value of this. This is going to give me the absolute value. Sorry, I should have. Right, if I do it consistently, then the red thing is the average. So at the left-hand side, I want the absolute value of the average squared. So my inequality should look like this. Okay, so now I take absolute values over here. Then on the left-hand side, if I take absolute values here, 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 then on the left-hand side, I'm going to get absolute values of x, and then, or norm of x, and then here I'm just putting the norms inside, and I'm using the uniform bounds. Okay, so let's see what that gives us. It's going to be an integral average on Q, still and then there's going to be a u, and then there's going to be gradient of eta. Gradient of eta is bounded by constant over alpha times L of q. And the u I just keep. Fine. And then for the other term, it's going to be constant times the average on q norm of eta, gradient of u, dx. Agreed on that? If I would do it like this, then I would have done something rather stupid, because I haven't kept track of the support, and I told you at the beginning that the support is an essential feature in this argument. Okay, so I should be more careful, and I should say that this function here, just as this function here, they have their support in q bar set minus, so they are supported in E, and E is Q, but you remove the inner cube. Okay? I should say maybe not support, but only non-zero only in. Okay? Because on these inner parts the gradient is 0. On this cube the gradient is 0, and this function is also 0. Okay? And if I take this information in account, my estimate is still correct, but I should put the characteristic function of E here, and I should put the characteristic function of E here. And then I'm fine, and I can use Hölder's inequality because I want to go to L2 averages. And so I use Hölder. Then it gives me C over alpha L of q. It's going to give me the integral of the characteristic function of E in L2 norm with respect to the average measure. So this is going to be measure of E over measure of q to the 1/2 times, well, if you apply Hölder's inequality here to get to L2 norms, you're going to pick up the average of absolute value of u squared 1/2, so this is going to be y 1/2. And for the other term, you're going to pick up C times measure of E divided by measure of q to the 1/2, and then it's going to be Z to the 1/2. Okay, so now you have to know how large these measures is. Right, so now I'm using parentheses, use that the measure of E over the measure of Q, well, what is it? It's measure of E is measure of Q minus measure of 1 minus alpha Q. So this is going to be just 1 times 1 minus alpha to the n. Okay, all the length of cube to the n factor out. Okay, so now comes for me a good moment, because since my analysis 1 lectures as a student, I was waiting for the moment that I would use Bernoulli's inequality. Never use it, but here I can use it. I can bound this by alpha n. It's just for entertainment. It's the first time I'm consciously using Bernoulli's inequality. Okay, so this alpha n, then I use this bound, right? This bound over here I use to replace this guy by alpha n, and this I replace by alpha n. Okay, and then I sort out terms, and I continue my estimate by saying, well, this gives C times n to the 1/2. And then there's going to be some terms in brackets. So the y 1/2 is going to come with, let's see, it's going to come with alpha L of Q, and then it's going to pick up alpha 1/2. Okay, and then the other term is going to come with C alpha 1/2 times Z. Okay, that's my estimate. This would be the estimate for x. Okay, I want the estimate for x squared, so I square everything. I do a 2 here. This gives me c squared, and it gives me n. It gives me alpha over alpha squared, so it gives me 1 over alpha squared length of cube squared. It gives me y, and the c I should have put out. It gives me alpha, and it gives me c. That should be my estimate. Good. So now the only thing I have to do is I have to optimize in alpha. You see now I have an additive bound with respect to capital Y and capital C. I optimize in alpha to make it a multiplicative one. So I choose conclude by picking alpha to be what? I think this is a game that you know by now. I want to have square root of y and square root of z on the right hand side. So the alpha goes with a c, so that's 1/2 of exponent too much, so I put a z to the minus 1/2 into the alpha. Then the alpha, wait, why did I put a square here? That was incorrect, right? That should be alpha. Because I had alpha 1/2 over alpha, so I had square root of alpha downstairs, and I squared is only alpha. It's not alpha squared. Okay, so this I should put here. Then I have the y. It's divided by the alpha. So division by the alpha already brings up the c 1/2. But I have too much y, so I should put y 1/2 in the alpha. And then everything is okay except that the scaling with respect to the length is not okay, because I should have 1 over length, and here I have 1 over length square, so I put the length of Q also in the alpha with a 1 over. Okay? And then you see, that's perfectly fine. It gives me here z 1/2, y 1/2, 1 over the length, and here it gives me y 1/2, z 1/2, and downstairs I have length to the minus 1 times length squared. So that's fine. Okay. So that's my proof. I know that some people in the audience like this trick. Should we make a break? Or do you want to think about my proof again and tell me if the proof is really done at this point? I've maybe sneaked in a mistake for you. Just a tiny one. Just a very, very tiny one. Is it okay to pick alpha like this? Go to the first line of the proof. Well, certainly alpha is positive. This is why I assumed that z would be positive. But there's an issue, right? Because I said that alpha has to be between 0 and 1. So who on earth is telling me that this choice is between 0 and 1? Okay, so let's take red chalk. Not yet, but almost. Because suppose that alpha would be larger or equal to 1. If alpha would be larger or equal to 1, this guy would be larger or equal to 1, so I could bound capital C 1/2 by 1 over length of cube times y 1/2. Just multiply the c to the 1/2 to the other side. Okay, then I would have this. And now I would have to bound x. I would have to bound x. Well, x is the average of the L1 average, so to say, without norms inside of the gradient. So I could use Cauchy-Schwarz or Jensen or Hölder, whatever you want. X in absolute value is less than z. X squared in absolute value is less than z. Just put absolute values inside and then use your favorite inequality. Well, z is the same as c1 half times c1 half, and if I have this estimate, then I can bound it by 1 over length of cube times y1 half times c1 half. So I have the correct inequality directly. Okay, so that case was actually much easier. And so the two cases together complete the proof, and we make a short break. Alright, so I cleaned the board for you. I need all the space, of course, for the second part of the lecture. Just to keep track of what we're trying to do, we had this splitting of the principal parts into two terms. It was last lecture, it was easy beginning of this lecture, and we're about to do the third term, and I already wrote the third term in a way where I introduced an additional averaging operator. And so the goal, as I explained to you, would be to prove a square function estimate for this guy. Okay, and so the next proposition says that this is precisely true. So proposition says you have the square function estimate with at 1 minus pt grad of u squared dt over t is controlled by constant times grad of u squared. Okay, and in particular we control square function estimate with gamma t times at 1 minus pt. Okay, this one was actually stronger than this one because you would just take this term, you bound this uniformly, and then you prove the square function estimate for the red term. Okay, red term is sitting here, and then that's enough. Alright, so the proof of this now it has very little to do with operators, at least with elliptic operators in divergence form, and it comes in two steps. Okay, so it brings us a little bit back to lecture 8. So step 1 used something that Andrew showed us when he gave the lecture on McIntosh's theorem. It's called a sure type bound. Okay, so I claim step 1 is a reduction of the claim to a sure type bound. Okay, so what I'm claiming here is that we have the following estimate. So suppose I can show the following. Oh, go away, guy. Right. I'm going to introduce additionally to these at minus and 1 minus pt operators, I'm going to introduce the qs operators because they gave us a reproducing formula in the last lecture, and I'm going to prove the following bound. At 1 minus pt qs of f is controlled by the minimum of s over t, and is it s over t the first one? Yeah, s over t, t over s plus t1 half over s1 half times f. Okay, this is what I claim, and in contrary to my claim in the proposition. Here f is really just L2 vector field, no gradient. On the left-hand side, the rows of T and S should be reversed. You're right. So it's like this. Thanks. Okay, so this is what I want to prove. Okay, don't be scared of the left-hand side. Just view this as a function theta of S over T, and then theta is going to be L1 on 0 infinity with respect to the Haar measure. Okay, so the theta function would just be the minimum of tau and 1 over tau plus 1 over square root of tau. So it has decay in 0, and it has also polynomial decay at infinity, so it's integrable with respect to the Haar measure. Okay, and so let us see why this 1317 implies the claim. Okay, to see that it implies the claim, I start with a reproducing formula. Okay, so I'm going to write gradient of u as the integral from 0 to infinity of 2 times qt star grad of u dt over t. Okay, and that was proposition or lemma 13.9.c. It was the reproducing Calderon type reproducing formula using the qt and their adjoints. Now, to this formula, I can apply as 1 minus ps. These operators are uniformly bounded with respect to t. Keep that in mind. These are just resolvents of the Laplacian. Also, these as operators are bounded on L2 uniformly in S. We keep that for later, because they're all bounded by the Hardy-Littlewood maximal operator times a function, times a constant depending on dimension. It's something we saw in lecture 9. So they are uniformly bounded on L2. For this argument, I just need the boundedness on L2. I use the properties of these Bochner integrals, and I can place the operators on the inside. All right, and so now I want to take L2 norms of the whole expression. So I take L2 norm here. I take L2 norm here. It's going to be less or equal. I take L2 norms here. Okay, and the way that I want to view this expression is, of course, to say that these are my operators from the Schur type bound, and this is my f. Okay. So taking this into account, I just square the whole thing, and I get that the square function I want to bound is the one with 1 minus ps grad of u 2 norm squared ds over s. I can bound this is less or equal times 4 times the integral from 0 to infinity, and then it's the integral from 0 to infinity again. It's going to be as 1 minus ps qt star grad of u ds dt over t squared on the outside ds over s. Okay, and so then I use the 13.17 estimate, and I bound it by, here there's a constant missing, of course. I bound it by 4 times c squared times the integral from 0 to infinity, and then another integral from 0 to infinity, and then it's going to be the theta function at s over t times qt star acting on the gradient in L2 norm dt over t squared ds over s. Alright, that's what I have. And now you have two options. Okay? In the lecture notes we call it the hard estimate. Either you go back to lecture 8 and you do what Andrew did using Cauchy-Schwarz and Tonelli twice, or you do what they suggested in the ISM forum, which is a completely valid way to see it. You view it as a convolution integral with respect to the Haar measure. Either way, what you're going to see is that this guy is bounded by, it's going to be the L norm, L1 norm in Haar measure of this theta function squared, and then it's going to be the L2 norm of the other function squared. So this is integral from 0 to infinity qt star grad of u squared dt over t. Okay, that's an estimate either you've seen before or you recognize it's Young's inequality on the multiplicative group 0 infinity with a Haar measure. Now this guy over here, this is just a constant because this function theta is integrable. Okay, this is just yet another constant. And what about this guy? Well, we had adjoint quadratic estimates earlier in today's lecture. The adjoint quadratic estimate in 13.9b says that this is bounded by the gradient of u squared by 13.9b. Okay, and then you see you control the square function exactly in the way that you want it. So I do not have to worry about the square function estimate anymore. I have to bound this mélange of operators here. And you see somehow this qt is an additional reproducing thing that introduces another parameter, and then you can play these tricks. And this is why these short types bounds have been useful in the section about H-infinity calculus, and this is why they're useful here. Okay, so step 2 is the proof of 1317. Now, how do I do this? And first of all, we're going to use that PT and Qt, they're uniformly bounded on L2. So uniformly with respect to t. I'm going to use that multiple times, and AT is the same thing. Okay. If you want the reference, this was Lemma 11.7. And these operators, the best way to understand them is in Fourier space. You should do the Fourier transform, and then they become equivalent unitarily to multiplication operators by nice functions. Okay, and so PS Qt under the Fourier transform, what is it going to be? It's going to be Qt. There's going to be resolvents, so it's 1 over 1 plus t squared m of xi. There's going to be a resolvent with the other parameter, 1 plus s squared m of xi, and then this guy has an additional t and a gradient, so it's 2 pi I t xi. This is the Fourier symbol corresponding to this operator. And likewise, if I do 1 minus ps qt, then I'm going to find two resolvents again. So I just copy them for you. Okay, and then I'm going to find 2 pi I t. I'm going to find the xi coming from the gradient, and then from the 1 minus resolvent ps you do the usual manipulation, and you see that there's going to be a s squared m of xi in the game. Okay, so the only thing that's important here is that these two guys, this gives this. Okay, and you see it by doing the usual +1 -1. You do +1 to this guy, cancels, gives the identity. You do -1, gives minus the resolvent, sits here. Okay, so these formula, they are correct. Okay, now I'm using this formula because I want to exploit symmetry when changing the roles of S and T in quite a funny way. Okay, so I want to have a formula that relates PS QT with PT QS, and I want a formula that relates 1 minus PS QT with 1 minus PT QS. Okay, now written like this, these formula are wrong. But let's have a look what happens. If I do PS QT, then I get the T. So here there's no symmetry, but then here I get the same expression. So if I multiply this expression by T, by S, then it gives me ST is the same expression as this guy multiplied by T. And in the same way, if I multiply this guy by T, then it gives me T squared S squared. It's the same as if I would change the roles, but I multiply by S. And then I bring the S and the T to the other side. And so I see that this gives me T over S, and this gives me S over T. Okay, and these relations I'm going to use. Okay, sometimes people call this thing, because it begins to look a little bit like a formalism, sometimes called the QT-PT formalism of Kaufmann and May. Now, I'm using this formalism to start bounding stuff. Okay, so the first case is when S is less than T. When S is less than T, then I'm trying to pick up S over T, because it's the smaller term. And this is easy, because AS 1 minus PTF, QTF, this is bounded by, well, this guy is uniformly bounded. Sorry, what did I want to do? Yeah, this guy is uniformly bounded, so I can just throw it away. So it gives me 1 minus PT, there is a S missing, sorry. 1 minus PS QT. Okay, 1 minus PS QT I can change for 1 minus PT QS at the expense of S over T. S over T is good because this is precisely what I want to have. So it gives me 1 minus PT QS applied to F. Well, PT and QS are bounded families of operators, so this is just bounded garbage. So this is bounded by S over T times norm of F. These are all L2 norms. And this is the good term. This is precisely what I'm claiming over there. So here I can already put the check mark. Okay. Now where's the other thing? Ah, there it's coming down. Okay. So the second case is when S is less than T. When T is less than S. Okay. When T is less than S, then I want to pick up T over S. T over S goes very well with the first formula in my green box over there. Okay, it goes very well with this first formula over there. But unfortunately, I'm not having this because there's a 1 minus PS. So I have to be a little bit more careful. So I start with AS 1 minus PS QT of F. Now, what should I do? I wrote you down this formula, so I would be stupid if I would not try to use it. And then I introduced the formula in the most brutal way. I just used the triangle inequality. I make it AS PS QT F plus AS QT F. Okay, and then AS is uniformly bounded. I can remove this. It costs a constant. And then PSQT, I can change the roles of the two guys thanks to the formula. So it gives me T over S times PT QSF for the first term, and for the second term I'm stuck for the moment, so I just keep it like it is. And then once again, this is uniformly bounded garbage. I can throw it away. It's T over S times norm of F plus AS QTF. Okay, so the T over S is something I want to see over there in 1317. So this term here is also a nice one. And what remains to be done is I need to bound the term with a dyadic averaging operator. Okay. So let's think about it. Remains to do AS QTF. AS QTF, what sort of function is this? What is it? Is it a function that takes enormously many values? Someone says no. It's constant. It's constant on a partition of Rn into cubes, the side length of which is S, more or less, up to a factor of 2. Okay, so if I want to compute this global norm, well, it's just a global norm of a step function, I just multiply the measure of the steps, of the supporting steps, with the value that the function takes. So if I do that, AS QTF norm squared, it's going to be a sum over all cubes in the partition, and on every cube I'm going to have the measure of cube times the value that the function takes, and the value that the function takes is the average on that very cube. So QTF dx. This is the definition of the integral at this point. And it should be squared, of course, because it's a L2 norm. Okay, so now Qt is T times gradient of Pt. Okay, so this here is T times gradient PTF. So that means I'm trying to compute the average of gradient fields on a cube. Now this is precisely why I showed you this lemma at the beginning of the lecture. Not at the beginning, before the break. Okay, we had the lemma that says precisely something about the average of a gradient field on a cube. Okay, and this is, if you want, so, before I go on with the estimate, just small digestion of what's happening here. This is the estimate where I'm not just brutally throwing all absolute values inside, but I'm using some sort of cancellation properties in my game. I'm using the cancellation properties of the Qt things. Remember that the Qt and the Qt star, they were giving rise to a reproducing formula, and at some point we said that these reproducing formulas, they work because in some sense there is some cancellation at some point. And the cancellation now is here hidden by the fact that we integrate a gradient over a cube, and when I integrate a gradient over a cube, I get some cancellation intuitively, because if the support would be inside of the cube, then I would get 0. Okay, so now let's apply the lemma in this situation. It gives me a sum over all these cubes, it gives me the measure of the cube that was just sitting there. Then this is average squared. So if we recall correctly the lemma, then it's constant over the side length, and then I get the product of L2 averages of the function and its gradient. Okay, so this gives me average on Q of T grad PTF squared. In the lemma, I think the U was first. Okay, so let's be like in the lemma, then it's T PTF 1/2, and then it's T grad PTF squared dx 1/2. Okay, that's what the lemma says. Right? Now, there's lots of things that cancel. For example, instead of the side length of the cube, I could just put a t, up to changing the constant. And then pt never goes well with a t. Pt always comes without a t. So I just pull out this t, gives a t squared 1/2. I can pull out this t precisely as a t, and I can cancel this. Okay, then these things are gone away. And then over there, t gradient pt, well, this is precisely undoing what I did here for you to recall to you that qt was a gradient field. This is just qt. And I can go on, because I divide by the measure of cube once with a power 1/2. I do it another time with a power 1/2. And over here, I multiply with the measure of q. So all of the measures of q also cancel. So this goes at the expense of making this a non-average integral and making this a non-average integral. Okay, so now that looks like this integral had some serious accident and it needed to be taped. The end result is that I get a constant times, oh, wait. You should have stopped me. Why did I say that? Why did I put a t over here? Sorry. This is an s. Sorry, this was an s. So the length was an s. So this t went out as a t. Sorry. You agree? There was cubes of side length s, so side length is s, but this was a t, so the t comes out, it gives me t over s. Oops. So it gives me constant times t over s. T over s is something that I like. I should not get rid of all the dependencies. Okay, so t over s goes there, but the rest was okay. The averages cancel the measure, and so I get integral of q ptf squared dx 1/2, and I get the same thing with q. All right. Now I'm going to use off-diagonal estimates. Okay. Now I'm going to split f as the union, as the sum from L equals to 1 to infinity over 1 of CLQ times f. I split f like this. I have L2 norm on Q here. I have the, for PT operators, I have the L2 norm for the QT operators. So I should probably write it like this. So this is PTF in L2 on Q, and this is QTF in L2 of Q. I split F like this, then I'm in the off-diagonal business, because PT and QT both satisfy L2 off-diagonal estimates. Alright, so if I apply off-diagonal estimates, then I can bound both of these terms in the same way. So it gives me the sum in all these cubes, and then it gives me the usual expression, sum going from L is equal to 1 to infinity, e to the minus c 2 to the L, f in L2 on CLQ. Okay, I would get it like this for this term, because I split the L2 norms. I have twice the same term, so I get a square here. You see it? Use the triangle inequality, put the f in here, use the triangle inequality in the off-diagonal estimate. It gives you a parenthesis of this type for this guy and for this guy too, so you get it squared. And then you're in business, because this is an estimate that you know how to do. You would use Cauchy-Schwarz in the L direction to put the square inside, and the square sits here. You sum up the L2 norms squared, you write it as an integral. In the integral you create overlap, because all of these annually, or the enlarged cubes, they were blown up by a factor. You do the counting exercise, it gives you power 2 to the L times n plus 1. This is still okay, because you have the exponential decay with a 2 to the L. You sum up the thing. In conclusion, this whole expression with all of the intertwined local L2 norms on these cubes, they will be controlled by the usual argument, by the global L2 norm of f. Okay, so usual argument says that this is less than Ts times f in L2 squared. Okay, and the usual argument is just this term is controlled by this term. It's the same one as in lecture 11 or at the beginning of the lecture 13. Okay, and so when you put it together, we started here, we ended there. It follows that ASQT of f in the 2 norm is less or equal, then you just take square roots. It's controlled by constant times T1/2 over S1/2 times f in 2. Okay, and this is a term we like. Look in the middle board up there. It's the term that we want. Okay, so here I can also make a check mark, and then the proof is complete. Beautiful. Do you have questions? Okay, so now I can quickly change the boards, and I go back to my general strategy. Now I can check mark this term, and I can say this was proposition 1313. Right, so hooray! We proved the principal part approximation, because we eliminated the smoothing. Before I write down what we have, there's a tiny remark, 3.14. You know, there was this trick where I introduced the AT operator, using that AT was idempotent. So AT squared was AT. So I could have gone one step further. Okay, because I could have said that the thing I want to bound, AT 1 minus PT, this is the same as AT times AT minus PT. Because this is AT, AT, AT-PT, AT-PT. Okay? I want a square function estimate for the left-hand side. I could have said this is uniformly bounded in T. And I could have just asked for the square function estimate involving the difference AT minus PT. Okay, and this is true. One could prove this. One could prove it, but it is harder in a sense that you have to do explicit computation with kernels and etc. etc. Okay, so in the lecture notes we wrote that even though the fact that I can also bound this, it renders very precisely the idea that the whole question in 1313 was about comparing dyadic and smooth averages. So the principle behind is much more transparent if we had bounded this one, but then I would have done much more tedious calculations using kernels of operators, computing explicit Fourier transforms, and so on and so forth. But for our purposes, it was enough to bound this term. Okay, and there's this beautiful paper of Axelson, now Rosen, Keith, and McIntosh, and we learned a trick to stick with this operator. Even though it's less transparent what it's actually doing, it's easier to bound and sufficient. So we learned the trick from there, and that helped us a lot. We could just use basically the symmetry properties over there rather than explicit kernel computations. Okay, that's just for the history. Now, all of these terms over there I have bounded, so the result that follows, and which is 1/2 way to the Kato problem, is the principal part approximation. And so even when none of the theta operators are given explicitly by kernels, it is still true that as in the TB theorem for square functions, I can bound theta of t minus gamma t AT acting on gradient fields in the square function norm by the norm of the vector field itself. Okay. So now I want to finish the lecture. So I see it's been a lot for you. Let us just put the things together and stop at a point where it's easier for me to resume next week. Okay, so I don't want to go through the principal part approximation again. I want to write down the reduction to a Carlson measure estimate. And so that's just a corollary of what we've been doing. So what do I want to say here? Let me think. I want to say that the following two things are equivalent. I can prove the Kato conjecture. This is what I want to do. Equivalently, I claim I need to show that gamma tx squared dx dt over t is a Carlson measure. Okay, that was precisely sort of the idea in the results of Chris, Journet, and Sems. Keep in mind that now the gamma t is a c to the n valued function, so absolute value as always is a c to the n norm. It's not difficult, it just follows from what we have, but I want to write down explicitly so that you get a second chance of grasping the idea. And also it's a good summary of what we've achieved so far as the Kato conjecture is concerned. So let's see. Why is this? Well, Kato is the same as proving the square function estimate with the theta function. Okay, that's been the reduction of Sylvie. This was 12.9. But now that we've bounded the square function with the principal part approximation, I can just take the difference with that, and I see that bounding this square function is equivalent to bounding the square function with a gamma t at, and in this square function s, before I write out explicitly the integration on Rn, so it's equivalent to saying that gamma t x dot at nabla u of x squared dx dt over t is controlled by gradient of u squared L2 norm. Okay, so now for sufficiency, sufficiency is what is interesting for us. Okay? Who cares in how many various ways I can characterize the Kato conjecture when in the end I'm going to prove it anyway. Okay? But so sufficiency, I want to outline a strategy how I can get there. So I want to see that if next week I'm going to prove to you the Carlson measure estimate, then I'm done. Okay, and for this direction it's easy, so I want to bound this square function. I just use the Cauchy-Schwarz inequality on R to the n, on C to the n, and I bound this squared by at grad u x squared times gamma t x squared. Okay, and then you see the gamma t x squared goes together with the dx dt over t. If this becomes a Carlson measure, then I can use Carlson's lemma component-wise, and I can bound the integration of dyadic averaging operator on this vector field with respect to the Carlson measure. I can bound it by the L2 norm of the vector field, and then I'm done. Okay, so claim by Carlson's lemma component-wise. Okay, that's the interesting thing for us. So it means next week Carlson measure estimate, and then we have it. Necessity, it's more of a gimmick, okay? But it's good to know because it says that we're not following a strategy that proves something ridiculously stronger. Okay, necessity is a gimmick, and we're gonna do it as an exercise. 13.1. Okay, so for you to figure out how that works, and that completes the proof of the reduction. So we have reduced the Kato conjecture to this Carlson measure estimate, and next week or next lecture I'm going to tell you what TB and T1 mean and how this technology can be used to achieve the Carlson measure estimate in the end and complete the ISOM lectures. Okay, thanks, and see you next week.